In this video, we will learn about Newton's third law. In the first minute, you'll find out what this law says and you will understand it conceptually. In the next 3 to 4 minutes, you will find out what is the main idea that you will be tested on. And in the rest of the video, we'll go over two very typical problems where Newton's law shows up, and we'll learn how Newton's third law applies to analytical problems, so problems that have to do with numbers. Let's firstly start by examining Newton's third law. What does it actually say? Newton's third law says that for every action force, there is an equal and opposite reaction force. So, for example, let's say I'm pushing down on my table with my fingers, right? So my fingers are pushing on the table, right? I'm applying the force on the table, so that is the action force, but the table is applying the force on my fingers, right? Because in my fingers, I'm feeling basically the force from the table. So this is the most maybe commonplace example of action-reaction force pair. Now, let me ask you a question. If every time we have some kind of force, some kind of action force, and we apply it, there is a reaction force there that is in the opposite direction, why don't action and reaction forces just cancel each other out? Why does anything in this universe move at all then? And why don't just all the forces cancel each other out? So this brings me to the main conceptual idea that you will be tested on. The reason why the action and reaction forces don't cancel out is because they are applied to different objects, right? So in the previous example, I was talking about applying the force on the table. So that's the reaction force. So that's the action force, and the reaction force is on my fingers, right? So they are applied to different objects. So action and reaction force are applied to different objects, so they do not cancel out. Guys, this is a very important idea, and you will be tested on this idea in various different forms in your quizzes and tests. So let's take a look at some commonplace examples. Let's say, for example, you're jumping off the boat. When a person jumps forward off a boat, the boat moves backwards. So the force that the person exerts on the boat, that would be the action force, is matched by an equal and opposite force that the boat exerts on the person, propelling them forward. So again, the action force is on the boat, but the reaction force is on the person, right? That's why if I'm pushing my boat backwards, right, I'm myself moving forwards. That is also the difference in action and reaction force are in opposite direction. Another example of this would be, let's say, if I'm pushing against the wall. So just the same way how we were talking about the table, right? If I'm pushing against the wall is pushing back and you, right? So I'm pushing on the wall, but the wall is pushing on me. Again, the forces of action and reaction force are applied to different subjects, as you see in this example as well. What about when you're walking or running, right? I'm sure you maybe haven't thought about Newton's third law when you were running, but maybe now next time you will. When you walk or run, your feet are pushing backwards against the ground, right? So your feet are applying the force on the ground, but the ground pushes back on your feet. Once again, as you see, the action and reaction force, right, are applied to different objects. But also take a look, right, that the direction of these forces is the opposite. So for example, my feet are pushing backwards, but the ground is propelling me forwards. Now, with this in mind, I want you to think about this next example, right? So if I take, for example, a rocket, right? Why does rocket engine point it downward? Because the rocket is moving upwards, right? But the rocket engines are pointing downward. How come? Well, it's because the rocket propels itself upward by expelling exhaust gases downward. So that is its action force. So its action force, right, is the force of rocket on the air, and the air is pushing upward on the rocket, right? So the rocket is pushing down on the air, but the air is pushing up on the rocket. So this is another very common, I see a lot of these examples with rocket launcher, so something to keep in mind. Finally, we'll see this example more with some of the analytical problems, right? But let's say when two balls collide, the force that the first one exerts on the second is equal that the second exerts on the first, right? If this doesn't make sense, it will, as we talk about the next analytical problem right here. So when the Newton's third law shows up in numerical problems is usually when there's multiple objects, right, interacting between each other. For example, problem 1 have to do with skater A and skater B. I know they have incredibly very original names. So let me draw our skaters. Just like all objects in physics, I will represent them by a box. So skater A has a mass of 50 kilograms and skater B has a mass of 60 kilograms, right? Great. So skater A pushes off skater B with a force of 100 newtons. So the force on B is 100 newtons over here. And the question is, what is the acceleration of B? Now that we have a free body diagram, now of course there is the normal force, right, and gravity, but they are not going to play a role in accelerating skater B. So if we apply the second Newton's law, it turns out to be a pretty simple problem, right? The only force is 100 newtons. The mass of skater B is 60 kilograms, so we can just divide both sides by 60. So 100 divided by 60 simplifies to 5/3 meters per second squared. So that's the acceleration of skater B. Now, where does the Newton's third law comes in here? Well, if skater A applies a force on skater B, then skater B will apply equal and opposite force, right, in the opposite direction, right? It really makes sense, right? If you imagine like you and your friend basically on an ice skating ring, if you push them with a force, right, you will also feel a force applied to you. So, and it's going to be the same exact force. So force that A is experiencing is also 100 newtons, but remember the reaction force is equal and opposite in direction, so it's to the left. So here, the second Newton's law is going to look like this. The only force applied in the horizontal direction is minus 100. The mass is 50, right? So if we divide both sides by 50, I get -2 meters per second squared, right? So it makes sense they have different accelerations because they have different masses. So now that we looked at this example, let's take a look at another very typical Newton's third law problem, is when a bunch of blocks are connected by a string. So in this problem, we'll have 3 different blocks that are aligned on a horizontal frictionless surface, just like this. And let me record the masses of these are as follows. Block 1 has a mass of 2 kilograms, block 2 has a mass of 3 kilograms, and block 3 has a mass of 4 kilograms. The blocks are connected by strings of negligible mass, and a force of 24 newtons is applied to block 1. So, okay. Let's say over here, a force of 24 newtons is applied, pushing all 3 blocks to the right. Okay, let's say to the left, it's okay. So we'll just consider that a negative direction. Calculate the tension in the string between the block 1 and block 2, okay? And the tension in the string between block 2 and block 3. So basically we need to find all the tensions. All right, let's take a look. How are we going to approach this problem? So the steps are going to be still the same. The very first step is always going to be to draw a free body diagram, right, for each of these objects. So here are the 24 newtons applied, and of course there is the tension force, right, in the opposite direction. So the tension force between the first and the second block, I'll call it T1. The second block, right, now of course there is the normal and the gravitational force for each of these blocks, but again, I'm not going to write that because it's not going to play into this problem solving. Now, what about the second block? The second block also experiences the tension, right? And the tension is going to be the same within this rope, so I'll also call that T1. And it will experience some other tension in this other rope that I'll call T2. Finally, the third block just experiences the tension because remember, there's no friction. So it just has the tension of T2, right? Great. So now that we have all our free body diagram ready, let's take a look. So firstly, what would be nice to figure out is the acceleration of all the blocks, because all of these blocks are connected by a string, so they're accelerating together. So in order to do that, the simplest would be to just consider them as a system. So consider all three blocks together. From that perspective, it's essentially like one giant block. I will ignore the tensions in between that is being pushed by the force of 24 newtons, right? So F net is really simple, it's just 24 newtons. The mass of these blocks, right? Since my system now is all of these blocks together, the mass is 2 plus 3 plus 4, right? Times the acceleration is what I'm trying to find. So 24 2 plus 3 is 5, plus 4 is 9, times a. So if I divide both sides by 9, my acceleration will be equal to 2.4 meters per second squared, right? Now, this is the acceleration. Now that we know acceleration, the acceleration will be the same for all of these blocks. So let me solve each of these blocks individually and consider them. So the first block, right, will have a force to 24 Newton force minus T1, right? In this example, since I started drawing first block on the left, right, I'm just going to consider to the left as being positive direction. So 24, right, minus T1 in the opposite direction, because again, it's accelerating, right, to the left, of course, is equal to M1 times A. So now, since my system, right, since I'm only making calculations for this block, the mass over here is going to be for this first block. So it's 2 kilograms times acceleration, which is 2.4, 24 minus T1. Or 4.8 minus T1. So if I rearrange this for T1, I should get an answer of, please roll a drum roll in the studio. T1 should be equal to 19.2 newtons. So that's my first tension, and I'm almost done, guys. So now we just have to calculate the tension in the second block, right? But we can do it if we consider, for example, the second block over here. So again, the second block has a tension to the left, T1 minus T2 is equal to M2A. Right? So what I'm doing here is, again, as always, I'm applying my second Newton's law to this problem. F net is equal to ma. Right? For the second block, there is the force of T1 to the left, T2 to the right. So I subtract them. Again, since I'm writing the equation for the second block, the mass in question, right, is M2. So let me just plug everything in. So 19.2 minus T2 is equal to mass of the third block is 3, acceleration is 2.4. So 6, 7.2. And finally, we're going to have 19.2 minus T. So 19.2, if I rearrange this, minus 7.2 T2, so the second tension is going to be 19 minus 7 is going to be 12 newtons. Finally, we have the tension in the second block. So this is another example of how Newton's third law could be applied, right, to solving these problems, since we have basically an action and the reaction force here, right? The tensions are the same in this block, so whatever the tension that this block applies on this block will be the same going both directions. Okay, so hopefully this example made sense, guys. Keep practicing and keep working through these problems on your way to an A. Thank you for watching, and see you in the next video.